quite a bit. So here we go, the moon part 1. So a few basic facts about the moon. Here's a full moon image that I generated using my 10-inch telescope a few years ago. Nearly full, there's a little bit missing up at the top right hand side there. But the moon is a quarter of the diameter of the Earth. It's very hard for us to tell, but that makes it quite a sizable solar system body. But a quarter to the power 3 is a 64th, and so the amount of material contained inside the moon is rather less than that of the Earth. And if we work out the mass of it, we discover that the mass of the moon is only 1/80th of the Earth's mass. So that tells us something about its density. Its overall average density is a bit less than that of the Earth. And we'll see why that is as we go forward. It orbits around the Earth, of course. The average distance, 384,000 kilometers, which is about 250,000 miles. And as we know, it almost always keeps the same face facing towards the Earth. So it rotates around its own axis at the same rate that it revolves around the Earth, taking a month to do each. Now, because of the elliptical nature of the moon's orbit, it's a little bit closer at some times and further away at others. And just tonight on the news, they're talking all about that and talking about supermoons, and it seems to have become a very popular thing for the media to get interested in. I personally find it a little disappointing that they make so much of it, because the difference really between a supermoon, when the moon is at its closest point, and a micromoon, as they call it, when it's at its furthest point from the Earth, is only 12% difference in the diameter. It does make it a little bit brighter than it would otherwise be, and it's really just a question of whether you get a full moon at the same point in the moon's journey around the Earth that happens to be the closest point to the Earth. So it's not really something that's all that rare, in fact. There's a little diagram here, though, a little animation that shows the moon over a period. You can see how it's rotating and wobbling, and actually we get to see about 57% of the overall total area of the moon. This is because, although it spins at a constant speed, the velocity around its elliptical orbit changes, with it moving faster when it's at the near point and more slowly when it's at the far point in its orbit, in accordance with Kepler's laws. And so sometimes that rotation gets ahead, other times it gets behind. And of course the orbit is tilted at about 5 degrees. So this phenomenon is called libration, and allows us to see just around little peaks around the corners, really, around the edge of the moon, to sometimes see some craters and little bits of terrain that we would not otherwise be able to spot. So I think this animation makes that point quite nicely. I've already told you the answer to this question, how far is it to the moon? And just to put that to scale, here's the Earth and the moon with the gap between them at the same scale as the size of the objects. So you can see there's really quite a lot of space between them, and the moon really is quite a long way away in comparison to its own diameter. Now, the first person to have a go at working out this problem and finding an answer was Aristarchus of Samos, and you can see one of his drawings here, and of course it's all in Greek, so we can't directly read it, or at least I can't, but the three circular objects that are represented there are the Sun, the Moon and the Earth, and he was working out geometry and different methods of trying to get an idea of how far away each of the bodies were and their sizes. So I can explain a little bit about his method. What he realized was that at half phase, the Earth, Moon and Sun make up a right-angled triangle. If we can see exactly half of the Moon, then it means the line from the center of the Moon to the center of the Sun is at right angles to the one from the center of the Moon to us here on Earth. So what he did was measure the angle between the Moon and the Sun in the sky, and he got an answer of 87 degrees, a very long, thin triangle. And from the shape of that triangle, he can conclude that the sun is 19 times further away from us than the moon is. You can't work out the absolute size of the triangle, but you can work out the relative lengths of the different edges. Now, the true angle for that angle at the Earth there is not 87 degrees. Nowadays, we realize it's actually 89.5. And the difference that makes is that it means that the sun is actually 400 times further away than the moon. It's an even longer, thinner triangle. The reason for the difference is that he was looking through the Earth's atmosphere, of course, and the Earth's atmosphere refracts images very slightly, and so you get that extra, 2.5 degrees that you need to allow for the bending of the light as it comes in. It also spotted the cosmic coincidence, though, that the moon and the sun appear the same size in the sky. The picture above there is of a total solar eclipse, where the black disk of the moon is just the right size to cover the disk of the sun. Again, of course, that varies slightly depending on whether the moon is at its near point to the Earth or a far point from the Earth in its orbit, its slightly elliptical orbit. But typically, it's just the right size. They're both about half a degree in the sky. And so Aristarchus concluded that whatever the ratio of the distances, the sun must be proportionally that much larger than the moon. So he would have concluded it was 19 times bigger than the moon. We would now make the same pronouncement and say that the sun must be 400 times further away and 400 times larger than the moon. And that is in agreement with all the other measurements that we have, so it's right. Then he looked at lunar eclipses, and I won't go into the details of the geometry and the mathematics because it's a little bit complicated, but he realized that by looking at how the moon passed into the Earth's shadow, as shown in the diagram above there, and the shape of the Earth's shadow carving across the moon, and the time that the moon spent being eclipsed, he could work out all the other parameters and end up with calculations that told him the distances and the sizes of the objects all individually. So he did a very good job of coming to all of these conclusions. He didn't necessarily get exactly the right answer, but the methods were very sound. Now, some 2,000 years later, the Royal Radar Establishment decided that they would have a go at measuring the distance to the moon. And in 1958, they bounced some radar beams off the moon and picked up the returning signals. And from the round trip delay and their knowledge of the speed of light, they worked out that the distance was 384,402 plus or minus 1.2 kilometers. Very much more accurate than any other measure to date at that time. And at the bottom there, as it says, the pulse was 2 megawatts of power being transmitted, so a very powerful radar signal. And each pulse lasted just 5 microseconds. Now, light travels nearly a mile in 5 microseconds, and so that's why the plus or minus 1.2 kilometers was the limiting factor in their ability to really resolve the distance. The slightly more up-to-date version of this is the Lunar Rangefinder, and this was left on the moon by Apollo. You've got the photograph there with the footprints on the moon around it, and this slightly angled array of prisms. They're right-angle prisms, so if you shine a beam of light into it, it bounces off the two surfaces and comes right back to you. And so, from Earth, we could fire a laser beam and aim it at this device on the moon, and the light would travel there and then be reflected and come back. And again, we could measure that, and using a laser and much more up-to-date measuring equipment, get very short pulses and therefore very accurate measurements of the distance. Now, the interesting part about that is that the laser beam, although it looks narrow and almost like it's not going to diverge at all, by the time it arrived at the moon, it was 6.5 kilometers wide, so spread out over quite a large area. That makes aiming it rather easier. You only have to get the reflector somewhere in that 6.5 kilometer diameter circle, but it does mean that the amount of power that comes back is really quite weak. So you needed very, very sensitive detectors to be able to pick the reflections up. But they were able to time it to 1 picosecond. That's 1 part in 10 to the 12 of a second, and measure the distance to the moon with an accuracy of 0.25 millimeters by doing this. So very, very precise indeed. And that's accurate enough to be able to trace the fact that the moon is spiraling away from us. It's moving away currently at about 3.8 centimeters every year. Its orbit is just getting larger and larger. And you can trace the theory back and realize that a long time ago, perhaps the orbit was much, much smaller. And indeed, it probably formed at a distance of 24,000 kilometers above the Earth. So really very close indeed. Now, the reason that the moon is moving away from us is because of the effect of the tides. It's a tidal drag. The angular momentum of the moon is being sapped because as the moon goes around the Earth, it pulls with its gravity the 2 tidal bulges in the ocean that you can see there. And due to the fact the Earth's spinning, the bulges end up being slightly offset from the direction of the moon. And so it creates a torque which tries to pull the moon into a different orbit. It also slows the Earth down, making our days longer. So several billion years ago, the Earth's day was 16 hours long, and now it's increased at a rate of about a microsecond a year to the point where it's now 23 hours and 56 minutes and 20 seconds. So it's the effect of the tides that's gradually driving the moon away. It was also the effect of the tides that's caused the moon to keep that one face pointing towards us. And if we look far enough forward in time, the Earth will be slowed down by this same effect to the point where the Earth also keeps one face facing out towards the somewhat more distant moon. But that's about 10 billion years ahead, so it's not something that we really need to worry about, mostly because the sun will have swelled up and eaten both of them by then as a red giant, but that's another story. So let's go back and look at the moon in a bit more detail. Here's that same picture of the full moon, and the first thing that you notice is that it has these dark markings on it. The Maurya, the seas of the moon, these smooth looking regions. Then it has highland regions that are peppered in brighter craters, and some of the craters have these very dramatic rays emanating out from them, some of which seem to go almost right around the moon, particularly from the big bright crater at the bottom there called Tycho. We'll have a look at that in a bit more detail in a minute. From an observer's point of view, you should always try and look at the moon at a variety of different phases. The full moon has this particular appearance, but at other times, like when it's a half moon, the shadows falling along the day-night boundary, which we call the terminator, are very good at picking out the detail. And you can see on this picture all sorts of detail in the craters there at the bottom. About a third of the way up, you can see the straight wall, which is just a sloping hillside, but with a shadow cast just by the effect of the crest of the hill there, making that straight line through what is a medium-sized crater. And then we go right on up to the top, where we can see the Mare Imbrium being cut in half by the day-night boundary and the crater Plato. We're going to look at that in a bit more detail. So here's a zoom in on some of the Maurya, and when we look at these, we realize they are actually all very much round and surrounded by a rim of mountains. and the floors of them are very small, very smooth indeed. This is, of course, why the ancient Greeks thought they might be filled with some sort of liquid and called them seas because of that smooth texture, but clearly not, because they've got substantial craters and other features on them that are permanent. But of course the reason is that they were flooded with molten lava at one point early on, just after they were formed, and so the smooth texture is the result of a liquid, so they weren't entirely wrong. Now the other thing that happens is that features on the moon get exposed to the solar wind, the harsh radiation coming from the sun, and this turns the lunar material darker with age, so that the Maurya, the seas, are very dark looking and they are very old, whereas the fresher material looks much brighter, and you can use this as a means of aging with the particular bits of terrain on the moon. Another way of trying to understand the age, though, is to look at the craters. Here's the southern polar region of the moon again, and you can see there are craters stacked on top of craters on top of craters. And of course, the ones that are right at the top must be the youngest, and they overlay the older ones. And so from the stacking order, we can work out which craters came in which order. And some people have obviously spent many hundreds of hours trying to sift through all of that and understand the relative ages of all of the craters. And we also notice that on the whole, the craters that are at the bottom are big ones, and the smaller craters tend to be quite numerous, but they tend to be in the foreground, so to speak. And this tells us something about the history of how the craters got there, in that in ancient times, long back in the dawn of the solar system, there was still quite a lot of big space rocks flying around, smashing into the moon and making these large craters. But gradually over time, the number of large impacts has diminished, and the average stuff that's been falling in later times has been all the much more common, much smaller space rocks, making many more small craters. In Mare Imbrium, here's a nice zoom-in picture of the region at the top of Mare Imbrium there, and the crater Plato. This is a crater, but it's got that very, very smooth floor to it again. And this is because it was flooded with molten lava. It's given it that very, very smooth appearance indeed. And just running away from it to the side there, you can see a wiggly little line. We'll talk about those in a minute. But also ringed on this picture is the Alpine Valley. It's quite a prominent feature to see round about half moon. And this is evidence of where two parts of the moon's crust have pulled apart. And much as the Great Rift Valley in Africa is the result of the terrain separating and falling down in the crack between, the same thing has been happening at some point in the history of the moon as well there. One of my favourite craters to show people during our public observing evenings on the moon is the Messier Crater. It's a crater pair, in fact. You can see them here, very bright. They're relatively young craters. And you can see the ejector leading from one of the craters down to the bottom left-hand corner there in a very narrow track. So what we think happened here is that a space rock came in and hit the moon, created the first slightly elliptical crater, bounced 20 kilometers and landed again, making the second crater, and then all the shattered ejector was projected off downrange. We've got an even better photograph of those two, so you can see the very elliptical nature of the first impact, and then the unsymmetrical second crater where the ejector was pretty much all gone one way. It really tells the story of it. So a very, very nice object to look at on the moon if you can find it. Here's that crater Tycho at the southern region of the moon there with its very prominent rays. It's very bright, and it's also on top of most of the other craters. that tells us its age is very young. It must be fairly recent, because not a lot has landed and obscured any of the features that it generated when it was created in the first place. And we think that the age for this is about 107 million years, which is nothing compared to the roughly 4 billion years of the age of the moon. We also see crater chains, quite a few of them on the moon here. Lots of crater chains. These are where some sort of incoming object, perhaps a comet, has been torn apart either by the gravity of the moon or more likely by the gravity of a larger object such as the Earth, and then smashed into the ground one fragment at a time and created these linear chains of craters there. In the middle of the seas, we see wrinkle ridges. You can see them picked out quite nicely in this particular photograph. And this is where shrinkage has occurred as the lava that flooded the sea area, the mare, cooled down. It then shrank, and that resulted in these little wrinkle patterns as the different parts cooled at different rates. What about volcanoes on the moon? Well, we do see some. They're pretty much extinct nowadays, we think, although some people seem to think they see occasional eruptions of something, of gas or something on the moon called transient lunar phenomena. I've never seen one myself, and I've never seen a decent photograph of one either, but perhaps someone will catch it in action one day. So you do find, in addition to all the impact craters, that there are these cone-shaped mountains that are obviously of volcanic origin, and they often have these wiggly lines, as you can see here, running away from them, and those are called rills or grabens. And here's a really good example of one running across the surface that's rather straight, but they often can wiggle around a lot, and they tend to stretch for quite long distances across the surface of the moon, particularly where there's been volcanic activity. And of course, what they are, lava tubes. Here's a lava tube in Hawaii. You can go down and explore it. This is where lava was running away from the active volcano, and the outer edge of the running lava, being exposed to the atmosphere, cools and forms a crust. But the liquid lava then continues to flow as long as the volcano is feeding it through the tunnel that has been made, until eventually the volcano stops erupting and the lava flows out the far end of these tunnels, and you end up with long tunnels underground. And of course, weathering and so forth can mean that the roof falls in, and that's what creates the rills on the moon. We think it also is responsible for these features we see called lunar pits. Here it looks like there is a lava tube under the ground, and the roof has fallen in this very nice circular fashion. I don't know whether that was the result of an impact punching a hole through or just the result of a collapse. And we've never really explored these, but it would be quite interesting to be able to send some sort of remote rover or something down into these pits and tubes and explore underneath the lunar surface a bit at some stage. Here's the same thing on a lava flow in Hawaii, where there's still the lava flowing in the lava tube underneath, but the surface has already fallen in. The same process creates these great long sinuous chains of what they call endogenic craters. Again, they're following the route of a collapsed lava tube. It took scientists quite a while to figure out what was going on with these interesting chains of craters.